All right, perfect. Great, so I think we can go ahead and get started. So today we're very happy to host Kjell Jorner for the last AI for Science seminar of the academic year. So Kjell is an assistant professor in digital chemistry at ETH Zürich. He was previously a postdoc at the University of Toronto working with Alana Spurugusic, and also a postdoc at AstraZeneca in the UK. And he did his PhD at Uppsala University in computational physical chemistry. Yes, okay, great. So today he'll be telling us about simulations and machine learning for molecular design and reactivity, and we're very happy to have him here, so take it away.
Thank you, Rocio. Just checking if can people hear us well online as well. Okay, good. Yeah, so thank you, Rocio, for the kind introduction. See if I can get this to work well. Sorry.
Maybe you have to just touch the.
It was working before when I. Oh, yes, probably. Exactly. Yes, so I'm the new professor at ETH Zürich since last year, beginning of 2023. So there I'm leading a group, we call ourselves the Digital Chemistry Laboratory. So it's myself and 5 PhD students, so 4 which have started already, and then we have Francisca, who is going to join us in August. Then I'm also fortunate enough to work together with a professor in the computer science department, Professor Krause, so I'm also a co-supervisor of 2 students from there. So here you can see us at a group excursion last year. This is Stefan, Dorian, Justino. Luca hadn't joined by then, and here you have Francisca. So this is a typical group excursion if you have your group based in Switzerland. So if you want to kind of follow the work of our group, and if you still haven't left X/Twitter, then we also have a group account where you can, we occasionally post things, for example, when we publish new papers. Also, if you want to join our group, you still have the chance. So we have a position open in the area of computer-aided catalyst design. So this expires later this week, so you have until Saturday to apply for this, or if you know someone who could be interested. So the, let's say, perfect candidate for this position would have a background in some computational science, for example, in chemistry, and also preferential machine learning, but also strengths in either of these areas, and willingness to learn the other part is also okay. So please share this. There's also the QR code if you want to have more information about that. So we're the group of digital chemistry. So you might be wondering, what is that? So we define this as an interdisciplinary research field. So we're taking, let's say, tools and methods from computational chemistry, from machine learning, from cheminformatics, and then we also want to make our tools available to other people. So we do software development, release the code on GitHub, pip, conda, and so on. Then chemistry is an experimental science. So if you want to have some impact in the long run, you also need to do experiments. We don't do experiments ourselves, but we work together with experimental groups. So that can be experimentalists working either kind of traditionally in the lab, doing wet experiments, or more recently doing high-throughput experimentation, and let's say in the near to mid-term future also so-called self-driving labs, which can run experiments rather autonomously. So what is our mission? What we want to do is to be able to accelerate chemical discovery using digital tools, and we have a strong core of our research in reactivity and catalysis. So there we're targeting, for example, reaction outcome prediction, reaction optimization, and the holy grail in this field, which is the catalyst and reaction design from scratch or from, let's say, good candidates. Then we also have an area where we're working a bit more opportunistically. So if we get the chance, and this is in the general area of computer-aided molecular design, where I myself have a strong background in organic electronic materials. We also have a new project, which is in the area of safe and sustainable by design. So these are molecules which have a certain functionality, but then there's also now increasing efforts in making these molecules, let's say, non-toxic and biodegradable already at the design stage. So a lot of people are now entering this field. You also see a lot of companies working in the area of, let's say, digital chemistry. So what is our niche here? What we want to do is to be able to work well with low amounts of data. And we can visualize this on a continuum. So on the left-hand side, we have no data, and on the right-hand side, we have lots of data. So if we have no data, usually we need to do simulations. And if we want to study reactivity and catalysis, we can do this through first principle simulations, what's called mechanistic DFT or density functional theory. If we, on the other hand, have lots of data, we can do deep learning. So we can train, for example, transformer models. And lots of data might mean thousands of data points or tens or millions of data points in the context of chemistry. On the other hand, usually we don't have that much data. So sometimes we can be lucky if we have even 100 data points for many chemical problems. So what we argue here is that you need to put more chemical information into the model. So you use, let's say, expert knowledge and prior information and so on. And this is increasingly in the field coming to be called chemistry-informed machine learning. So we have a number of different approaches for doing this. One is a bit more traditional. That's based on what's called chemical descriptors, usually calculated with quantum chemistry. But there's also a number of different approaches which are emerging where you can put this type of chemical information directly into deep learning methods. And we can call this then chemistry augmented deep learning. So what we are aiming for is to, let's say, developing and applying methods which lie in this area. So within Switzerland and within ETH, we're very closely associated with catalysis and one very big research consortium in this area, which is called the NCCR catalysis. So the mission of the NCCR catalysis is to, let's say, accelerate the transition of the chemical industry to go from the current status quo, which is using, let's say, petroleum feedstock to make all the chemicals that we need, and instead being able to do this from renewable feedstocks. So to do this, it's quite a challenging task. You need a lot of different expertise. So we have basically all the way from being able to activate small molecules experimentally, such as CO2, all the way going towards the implementation. So how can we scale this up? How can we do the techno-economical analysis of the technologies and so on? So we are a part of this, and we're part of the digitalization package. So how can we actually use machine learning? How can we use computational methods to make this transition faster? We're also part of the ETH AI Center. So this is a center which we have at ETH, which brings together people from computer science. So people who are, let's say, theorists and expert in the methodology, with researchers such as myself who are experts more in the applications, for example, AI for sciences and engineering. And there we're very fortunate to work together with Andreas Krause, who was also the chair of the steering committee of the AI Center. So that's a bit about the group, the background and so on. So now we'll be going a bit more into the science. And first I will be talking generally about computer-aided molecular design, then showing one application of computer-aided molecular design with a very simple quantum chemical method, which is called Hückel theory. Then I will talk about how we can design what's called singlet fission materials, which could be used in, for example, solar cells, and how we can do this with what we call uncertainty-aware genetic algorithms. And then finally, I hope I have time also to talk about some reaction design, which we're doing with the help of reactive force fields. So first, something about computer-aided molecular design, if you're not familiar with this. If you want to have some type of application, for example, you want to make a drug or a catalyst, you would need to start with, let's say, the problem that you want to solve. So if you want to have a drug, we would like to have some medication which we can give to people. This is a quite complicated product which contains a lot of different constituents and also requires a lot of formulation and so on. But we can also simplify this and look just at the molecular level. So we would need something which could, for example, bind to a protein in the body. And we call this the active pharmaceutical ingredient. So usually we don't know how this looks like, so we need to design it. And if you look at how this is done today, this is done by combination of different methods. So one very important aspect here would be the human expertise, so the medicinal chemists and their accumulated knowledge. Then we have a lot of, let's say, trial and error, a lot of iterations. And our hope is that we can also, in this area, contribute with, for example, computational tools, which could be based on first principles, but also increasingly more, let's say, machine learning or AI-based design methods. So the idea is that with this computer-aided molecular design, we would be able to integrate this and we would be able to accelerate this process. So the holy grail in this field is something that we call inverse design. So we can contrast this with what we normally do, which is direct design. So in the direct design, we have some kind of property that we're interested in. We can call this Y. We test different molecules. We can call them X. And then we kind of try to iterate this until we find something which works well. So the promise of the inverse design is that we can instead kind of try to optimize this Y directly and say, okay, we want a certain property. And then we would be able to have some inverse of this function here so that we can kind of back translate this to a certain molecule which would have these properties. So this is a bit of an abstract concept, but I can show you in the next slide how it would work in practice. And then you can also have hybrids of this, for example, high-throughput virtual or experimental screening, which can also accelerate chemical discovery. So one reason why you need this inverse design is that the chemical search space is very large. So if you just think about, let's say, small drug-like molecules, this can easily reach a space of 10 to the power of 60 different molecules. So it's actually quite difficult or even impossible to search this just by doing experiments. So we have a number of these methods which are available. So we have both traditional methods such as genetic algorithms, and then we have more modern methods which are based on deep learning, such as variational autoencoders. And let's say the purpose of all these algorithms, it is to suggest new molecules which have these desired properties. So you can, let's say you can see these algorithms as some kind of idea generators, and then you can follow up on these ideas later. So in my view, it's, let's say, not too important exactly which of these generators you use, but what is actually very important is how you can evaluate these molecules. So at the heart of all of these generative models or inverse design models, you would have some type of property predictor which would tell you how good a certain molecule is for a certain application. So in the genetic algorithm, you would use this as a fitness function. And in the variational autoencoder, this would be a property predictor which could help you to shape your so-called latent space. And then you can use techniques such as gradient optimization. So the general rule is if you have a very good property predictor, you can get good results out of these algorithms. And if you don't have a good property predictor, you will probably just get a lot of crap, which will not help anyone. In my view, the most important part is this predictor. So the question is, what type of predictors do we have? So one type is machine learning. And machine learning would be very useful because it's very fast, and under some circumstances, it can also be very accurate. The problem, however, with machine learning is that it cannot generalize so well, at least the methods that we have today. So in chemistry, we would say that these have a limited so-called applicability domain. We can also do simulations. So the advantage here is that we have a wide applicability domain, but on the other hand, they are too slow. So we cannot really use them effectively for the inverse design. Then I think it's also very important to remember that even though you do a simulation, this might be based on sound physical principles and so on. It might also be that your model of the system is wrong. So you might actually be simulating the wrong things, and this might actually then not help you in the end anyway. Something which is very exciting nowadays is that we also have these hybrid models which are emerging, which are basically taking the best of both worlds of machine learning and physics-based simulations. So these would be super neat if we have them, but they are also now, let's say, just being developed in the literature, so they are not generally available. So something else which is not, let's say, acknowledged too much is what we can call so-called hybrid light models. So these are models which have actually been used a lot already in chemistry, so we call these semi-empirical methods. So they are based in part on physics-based simulations, but we also have parameters that we use. The advantage is that we don't have too many of these parameters, so the models are still able to generalize to a larger extent. So I will be talking about the application of some of these models later in the talk. So what's the problem with the property predictors based on machine learning? So I think we can understand this in terms of this Goodhart's law, which says that when a measure becomes a target, it ceases to be a good measure. So basically these inverse design algorithms, be it a genetic algorithm or a deep learning method, they are, let's say, experts at exploiting these property predictors and exploiting the imperfections in them. So in chemistry, we understand this through the lens of the so-called applicability domain. So the applicability domain is quite an abstract concept, which basically tells you when you can trust your machine learning model and when you cannot trust it. So in one dimensions, it could look something like this, that, okay, you trained your model on this domain here, and then you would not be able to trust it to extrapolate to some new domain where you didn't have training data. We can also extend this into multiple dimensions, also in a rather abstract way, and we can define some domain where we would be able to trust the model. So we would say that it's inside the applicability domain. And if we are making predictions for some other molecules which are outside the applicability domain, we would not be able to trust these predictions. From the machine learning perspective, we also have similar concept, let's say. So one of these is what we can call adversarial examples. So they can be, for example, obtained by optimizing certain inputs to give certain outputs from machine learning classifiers. So here's one example where they have done this for image classification. So for example, you might not think that this is the most representative electric guitar that you have seen, but your classification algorithm thinks that it's actually quite a good electric guitar. We can also see this for molecules. So if we use, let's say, quite naive property predictors, then these generative models, they will quite soon learn to exploit these quite naive property functions. So for example, penalized log p is a property which has been used, for example, to approximate drug likeness or drug design. And if you give this to generative models, they will soon come up with these chains of sulfur atoms and phosphorus atoms. So they fulfill this criterion, but they are probably not what you would like to give as a drug. So this can actually happen to even quite sophisticated scoring functions, even those which are based on some kind of, let's say, empirical physical formulations such as protein docking. So all of these molecules are generated to optimize a docking score, but it's probably not something that you would like to ask a chemist to synthesize in the lab because they are all extremely unstable and could not be made. But it's also very highly doubtful that they would even bind to the protein to which you did the docking to. So it's very likely that they are just exploiting some deficiency in this scoring function. So we can call this generally, let's say, that we're kind of hacking this property predictor. So there's a number of different papers where they show this in action. So here they have actually done, I think it is not sure if this was docking, but some type of scoring function where they actually have a ground truth. So they run a genetic algorithm, and then they can see that the molecules, according to the scoring function, they get better and better. But if you compare to the ground truth, it actually doesn't improve very much after the initial steps. And it actually even starts decreasing after a while. Here's another paper where they have done another trick. So they basically take a data set, they train a machine learning classifier on this data set, and then they do optimization. Also here, I think with for example, genetic algorithm or with language models. And they have a machine learning model which is kind of steering the optimization. So that's the blue curve here. But they also have a number of control models. So one control model is just a machine learning model of the same type, which has been trained with a different random seed. So it's in principle trained on the same data, it's just slightly different. And you can see that these quite soon diverge. So this is an indication that the generative model is kind of starting to exploit peculiarities in this particular machine learning function, which was trained with this particular random seed. And you can see this even more clearly that if you take another sample from the same data set and use that as training data, then the effect is even stronger. So we can also see that this is getting worse when we go to even larger chemical spaces. So this is an example where they have studied docking, and they have studied in very high dimensions, so like billions of different compounds. So they identify something what they call artifacts. So the artifacts are, let's say, very serious offenders. So they are molecules which you can basically look at and say, okay, this molecule is wrong or doesn't really fulfill the criteria. So they can see that these artifacts, they start to dominate when you go to the very large chemical spaces, so up towards millions or billions of different molecules. And if you would have something like a goal-directed generative model, such as a genetic algorithm, they would quite quickly become dominated by these artifacts, which are basically false positives. So if you would go to the large millions or billions size, then actually, if you look at like top 100 or top 1,000 molecules, they would all be dominated by artifacts. So this is a bit of a motivation why we don't really want to work with pure machine learning. So we go a bit more towards simulations or combinations of simulations and machine learning. And will give you one example how we do this with Hückel theory, which is a very simple quantum chemical simulation method. So this is a computational method. So what we need to do there is that we have our real world, which is basically in the lab. We would need to translate this to some atomistic model, which we can study with our tools. And then we would need to translate this atomistic model into a mathematical model, which we can actually then solve in the computer. What we do in practice is that we will solve the Schrödinger equation. The Schrödinger equation will give basically the energy of our molecular system as a function of the molecular coordinates. So this is a three-dimensional space. Here's, let's say, a two-dimensional simplification of that. And then we have different molecules and different isomers of the molecules which live on this three n-dimensional surface. We can calculate how stable they are. We can calculate, for example, transitions between different compounds in the form of chemical reactions. We can also calculate electronic excitations. So, for example, how these molecules would absorb light, and also, for example, how they would react if they have absorbed light, so photochemistry. So what we basically need is some kind of mathematical function which takes in the coordinates of our system and gives us these energies. And we have a number of these methods. So we have, let's say, a hierarchy based on how expensive they are. So on the left-hand side here, we have what we call classical methods. So these are based on force fields, so very simple classical terms for energies. And on the right-hand side, we have very expensive computational methods which try to solve the Schrödinger equation more exactly. Then here we have one quite exciting development, which is what we call machine learning potentials. So these are machine learning models which have been trained on this higher level data. And if you construct these in a sufficiently good manner, you can actually get something which sometimes can even generalize quite well. Another form of this, which I showed on a few slides back, is what's called the semi-empirical methods. So these are, let's say, old style hybrids between the simulations and machine learning. So they are sometimes heavily, sometimes less heavily parameterized models. And we can also see here that we have some kind of divide here. So if we want to do inverse design or computer-aided molecular design, we would prefer to stay on the left-hand side here rather than going on the right-hand side, because these methods are generally too slow for us to use. So what can we use these methods for? We can actually simulate a lot of chemical properties. So we might, for example, simulate drug binding energies. If we have, for example, we want to make batteries, we could simulate redox potentials. Something that we'll be looking at in this lecture is especially like UV-Vis properties. So these are how do these molecules absorb light and what happens to them after they absorb light and so on. But in principle, we can use these methods to simulate a lot of stuff. So we can use them directly in these inverse design algorithms, or we can also use it as training data for machine learning models. So one method that we have been using is actually extremely simple. So this is called Hückel theory. This is one of the first molecular orbital theories to solve the Schrödinger equation, which was developed in the 1920s and 1930s. So we're trying to solve the Schrödinger equation. To do this, we basically take our molecule, the molecular graph. We have different types of atoms. They have different connectivity. So we take the adjacency graph of this molecule. We construct the matrix. And then we have parameters in this matrix for different types of atoms, for example, carbon, and different types of bonds, for example, CC bonds or CO bonds. So these correspond to what we call one electron integrals in the Schrödinger equation. And what we do in Hückel theory, this is a semi-empirical method, so we would just replace these with the values of the parameters. Then we can diagonalize this matrix, and then we can get properties of the molecule. So we can get the molecular orbitals, so where the electrons basically live in the molecule, and what energies these electrons have. And based on this, we can calculate the energy of the molecule, but we can also, for example, calculate the electronic excitation between the HOMO and the LUMO. So this is extremely simple. We just need these parameters. We diagonalize this matrix, and then we have some results. So you might think, okay, how useful can this actually be? So under quite favorable circumstances, if you study, let's say, stay within certain classes of compounds, it can actually be quite good. So you can, for example, get reduction potentials from these LUMO energies and the oxidation potentials versus these HOMO orbital energies. And you can also study photoexcitations. So you can get this from the HOMO-LUMO gap. So this is a bit cherry-picked, but under, let's say, favorable circumstances, it's actually not that bad. So one application where we have used this is to study molecules which are aromatic. So this is a quite important property in chemistry. So molecules which are aromatic, such as the benzene molecule, they have electrons which are cyclically delocalized. And this makes these molecules both, let's say, unusually stable, but it also gives them some certain properties which make them useful, for example, for organic electronic materials. So to calculate aromaticity, we will first explore an alternative solution to this Hückel problem. So we saw that we can take the molecule, and if we have only carbon atoms, we have a very simple expression for this. So we take our molecule, we have the adjacency matrix, these are parameters, and then instead of diagonalizing, we can construct something called instead the characteristic polynomial. So basically it will give us the same orbitals and so on as the diagonalization, but we get it instead as the solution to this polynomial here, so the different roots of this polynomial. So why are we doing this? It's because we want to calculate aromaticity. And we're going to do this through special formulation of Hückel theory, which is based on graph theory. So we have something called the graph theory of aromaticity, which was developed in the 1970s. So it's one of these cases in science where you discover something independently at different places. So this was discovered in Japan by Aihara and in Croatia by Trinaistic and Gutman. So what they do is that they do a graph theoretical treatment of Hückel theory. We have the energy of our actual system. We get that one by solving this characteristic polynomial. And then we need some kind of reference system which does not have this cyclic conjugation that aromatic compounds have. So the problem here is that we know everything except how to construct this reference system. So how do we do that? Long story short, we use a formulation for, let's say, decomposing this characteristic polynomial, which was also developed in the 60s, which is called Sachs subgraphs. So you can take the characteristic polynomial and then you decompose it into terms which basically depend on the molecular graph. And they have two types of terms. One are non-cyclic and some are cyclic. And in this theory, you would say, okay, we're interested in the cyclic conjugation. So we just cross out all these guys which correspond to cyclic terms. And then we get another polynomial when we delete these guys, and we call this the reference polynomial. So what we can do is to solve this polynomial, the real polynomial, and the reference polynomial. And then we get the energies. We can calculate the total energy of the molecule by filling up the electrons and so on. And then we can calculate some energy difference. And this will be a measure of the aromaticity of the molecule. So we have basically a semi-empirical method, which would allow us to get a number for how aromatic a molecule is. And then we want now to optimize. So we want to find the molecules which are the most aromatic or which are the least aromatic. And to do this, we're going to use a genetic algorithm. Basically, we have some population of molecules. They are going to look something like this. We can calculate their fitness. That's this topological resonance energy, the measure of the aromaticity. We do some selection. We remove the worst ones. And then we will replace the ones that we removed by this crossover and mutation. So we can, for example, generate new molecules by adding rings, removing rings, replacing atoms, and so on. And by running this genetic algorithm for many times, we can then successively get the population which has, for example, more or less aromatic compounds. So these are some of the results. So if we stay in the electronic ground state, so this is a non-photoexcited molecule, a normal molecule, the genetic algorithm quite quickly discovers that benzene is actually the most aromatic molecule which you can find. So this kind of makes sense also from a chemical point of view. If you're in the excited state, let's say we have not fully analyzed these results yet, but we get something which is decidedly not benzene. We tend to get a more extended pi conjugated system here, and this is potentially something that we can also further analyze to try to get some insight. If we go to trying to minimize, to try to find, let's say, the molecule which is the least aromatic, in the ground state, we start forming these very long acenes. And these are actually known from the literature that these molecules are quite unstable. So they're very difficult to make and they quickly decompose. This also makes sense. And if we go to the excited state, we again find benzene here. And that's also quite well known that benzene is especially unstable when it is photoexcited. So it seems that the genetic algorithm is actually performing according to the expectations, or at least according to our chemical intuition. So that's one application of Hückel theory. So now I will show another one. And here we're going to construct what we can call a hybrid model. So we have neural networks, and we can combine neural networks, which are coded with some auto-differentiation frameworks, such as PyTorch, JAX, TensorFlow, and so on, with a differentiable physical model. So what we're basically going to do is to take our Hückel model, we make it differentiable, and then we would treat this as some type, let's say, like a neural network with certain parameters and so on. And in the future, these can also be combined, and there's a number of examples of this in the literature as well. We're not going to go to this stage yet, but we're going to stay at the level of the differentiable model. But this is a very natural extension, how you can take a physical model and also combine it with a neural network. So we take everything as we did previously. We have our Hückel model, we can solve this and so on. And the only thing is that we code this up in a auto-differentiable framework, in this case JAX. And what we can then do is to use the tools that we can get from modern neural network methods. So what we can, for example, do is to compare these properties that we get from higher level computations, and then we can use these to back propagate errors to the parameters here and update them. But we also will be able to do something else, which is actually to optimize the identity of these atoms. We can do what's called alchemical optimization. So it's actually not too complicated to do this change. So if you use JAX, you can replace a lot of functional calls of NumPy to the corresponding ones in JAX. So for example, if you do eigenvalue decomposition, you can use the corresponding function from JAX. So there's a lot of other code for actually making this work in practice, but in principle, it's not too difficult. So one thing that we can do with this, which is quite exciting, is that we can do this alchemical optimization. So we can take a molecule, for example, this coronine molecule, and then we say that some of these atoms, we fix them as carbon atoms, and some of them, we allow them to vary between carbon, nitrogen, and phosphorus. And then we would say that, okay, we let these, the identity of these atoms vary as some kind of weighted sum. And then we will be able to optimize this towards some optimum with respect to certain properties, for example, the homolumo gap or other properties such as the polarizability, which is a second order derivative, which we can also very easily calculate with the auto-differentiation framework. So we can see that this works. So for example, if we randomly initiate these atoms with random weights, we can see that by optimizing, we can significantly lower the homolumo gap, or we can increase the polarizability. So you can see this in action. So here we have one molecule, pyrene, that we're optimizing, and you can see here in action the optimization of parameters. This line with the feasible one that indicates basically that for the real molecule, we cannot have something which is like 50% carbon or 50% nitrogen. We need to pick the most, let's say, probable atom based on the weights. So you can see that the model basically optimizes some of these to be phosphorus and some of them to be nitrogen to minimize the homolumo gap. So that's a bit what we can do with, let's say, a very simple quantum chemical theory, Hückel theory. So now we'll be using another approach, which is based on actually machine learning. And here we'll be using a genetic algorithm for doing that. So this was a collaboration between my group and the group of Clémence Cormenboeuf at EPFL in Switzerland, and which was carried out by Luca Schaufelberger, who was a master student, who then later joined my group for his PhD. So here we're looking for a class of molecules which are called singlet fission molecules. So these are molecules which could potentially allow us to make solar cells more efficient. So the problem with solar cells is that they have a certain band gap, and we cannot use the energy of photons which have an energy which is higher than that band gap. So what happens in a singlet fission material is that these high energy photons, they excite some molecule which goes from the singlet ground state to the singlet excited state. Then this singlet state, it breaks down into two lower energy so-called triplet states. And these triplet states, they have the appropriate energy to be injected into the semiconductor of the solar cell. So basically, you take these high energy photons, which you cannot use, and then in the end, they are injected into the solar cell. So you can potentially increase the efficiency. The problem is that we don't really know too many of these singlet fission materials. They are very rare. So what we wanted to do in this project was to try to find more of them. To do that, we again use a genetic algorithm, but in this case, we work in a fragment space. So we don't kind of allow the molecules to be optimized in an unconstrained way, but we break the molecule apart into 3 different parts. So we call one of these the core, and then on the core of the molecule, we can have 2 different substituents. Then we run our genetic algorithm in the same way. We have a population, we calculate the thickness, we do the simulation, then we replenish the molecules which were removed, and so on. And by running this many times, we would get better and better molecules for singlet fission. So what are these genetic operations in this case? So we have what we call mutation. So in mutation, we would take one of the substituents or the core in the molecule, and we would replace this from a fragment pool. And I will explain on the next slide where we get this from, but it contains different cores and it contains different substituents. We can also do crossover. In crossover, we take 2 of the molecules from the population, and then we, let's say, mate them, and they give 1 child molecule as an offspring. And this child molecule, it will inherit properties from both of the parents. So it will inherit substituents and cores in, let's say, a random manner from both of them. So this is how we can replenish the population. So we have the genetic algorithm. We need a number of components to be able to run it. So one is this pool of different fragments, so the substituents and the cores. And we get these from a database, which is called formed. And then we also need to be able to calculate the fitness. And we do this, in this case, with machine learning models. And these machine learning models, they predict both the energy score, which is important for the singlet fission materials, but we also include aspects such as how easy they are to synthesize, and also some characterization of the excited state, which is important for these properties. So the question is, why can we use machine learning in this case? Isn't it very bad for generative models? So in this case, we are actually running it in a quite constrained space. So we have this fragment space, which is basically the formed library. And we would also train the machine learning models on this database. So it hasn't seen all the molecules that have been generated, but it has seen all the different fragments. So it's actually being able to generalize a bit better. So we have the components to be able to run the genetic algorithm, and we can run it in one of 2 different modes. So this is what we call an uncertainty-aware genetic optimization. So we have a machine learning model which gives us some uncertainty, and then we can tune this between, say, an exploitation mode and an exploration mode. And in the exploitation mode, we want to kind of stay in a certain chemical space, try to find better molecules which are similar to what we already have. In the exploration phase, we try to completely find new and interesting molecules. So we can run this genetic algorithm. We run it many times in these 2 different modes, and then we can collect all the candidates and then further kind of validate them and see that they actually correspond to what we want. And then in the end, the goal here would be to do some experimental testing to actually see if they work or not. I will come back to that later. So let's see. I think someone was maybe drawing something on the slide. Yes, I think it's working now. Yes. So here is one example of how we can run the genetic algorithm. So what we have here on the x-axis is the generations that we have run the genetic algorithm, and on the y-axis we have these different scores that we're trying to optimize. So here we're trying to maximize this energy score, we're trying to minimize this synthetic difficulty, and we're trying to maximize this whole electron distance. And this genetic algorithm is run in a hierarchical mode, so it tries first to kind of satisfy this energy criterion, then moves on to the next objective and so on. So here is one example where we can actually see some type of discovery event here. So the genetic algorithm rediscovers this Bo-Dippy core, which is actually a fragment which has been previously suggested for singlet fission. And you can also see that the molecules which are generated after this discovery event here are actually quite chemically distinct from the molecules which were generated before. So this gives you some indication for how we can run the genetic algorithm, what it can lead to. So we run this in many different ways and many different times, and then we gather all the molecules which would be promising.
What you would explain what the difference between the exploitative and explorative phase of the generation is.
Oh, yes, okay. Can maybe go back. Yeah, so basically here it's like, so in the fitness function, we would also consider the uncertainty. And then this would be some kind of lower confidence bound or upper confidence bound optimization. So here we would optimize for mu minus 2 sigma. So we would basically say that something which has a lower uncertainty is favored. And here we would say that something with a higher uncertainty is favored. So that's kind of the two modes that we use. Okay. Yes, so we can run it in these two different modes. So we have the exploitation and we have the exploration. So in the exploitation, we can actually rediscover some fragments which are already known to be good for singlet fission. So that's these tetracenes, anthracenes, Bodippy, and so on. But maybe more importantly or more interestingly, we can also discover new fragments which have not been studied before. So we could take this and look at them a bit more in detail and see if we could actually understand what is going on. So it turns out that a lot of these compounds are what we call meso-ionic acceptors. So this is a quite exotic family of molecules. So they have these what we call resonance structures, which are charge separated. So you cannot draw the normal charge neutral resonance structures. And also, if you look at the excited states, they feature what we call a charge transfer excited state. So you move the electron within the molecule, but the triplet state is locally excited. And this is also a property which is potentially useful for singlet fission. So what we could then do in the next step is that, okay, we identify this class of compounds as potentially interesting, these meso-ionic acceptors, and say molecules which were similar to them. And then we could scour this database formed for all of these fragments. So this is, let's say, a lot of fragments which were not probed initially, also by the genetic algorithm in all different conformations. So we will take all these fragments, then we combine them with a certain donor group, which is the bi-thiophene donor. Then we could screen it with the same methodology that we did for the genetic algorithm. And then we would further filter them with the more expensive DFT simulations. And in this way, we could identify a new batch of candidates, which are potentially even more promising. So this one, number 12, also has this property that it has the charge transfer excited state and the locally excited triplet state. And this one is also interesting because it's actually quite simple to synthesize. So this is something that we're currently going to explore together with experimental collaborators, or even as we speak, potentially trying to synthesize this one. So I was thinking, should we stop for some questions? Yeah, okay. Yeah, I'm just thinking maybe depending on the time, if we have time for the last part, or if it's better to provide time for the questions.
We have 10 minutes left,
yeah.
So maybe it's a good point to stop. I think to leave some time for questions, or I mean, it's up to you if you prefer to.
Yeah, I mean, I have maybe 10 slides left or something like that. So, but maybe it would be better because it's a bit of a different topic, the last one. So maybe we can stop here and see if there's any questions.
Yeah.
Are there any questions? Or any questions in the
Yeah.
So this is mostly a question of curiosity. You mentioned during the introduction that there are these hybrid methods, right?
Yeah. Yes.
Then you brought up semi-empirical methods as an example of a very light hybrid method.
Yes.
Do you have any examples of a heavy hybrid method?
Yes, let's go back and look at this. Yeah, so I mean, you can see this like Hückel method as a very light hybrid method in a sense. So I mean, in principle, you would calculate these guys here from first principles. You can do this with like Gaussian orbitals and so on, but here we just replace them with numbers. So I mean, it's a type of empirical method. Then you can also have much more advanced semi-empirical methods where you have thousands or hundreds or thousands of parameters, and these kind of approaches some type of machine learning method in a way. What you can also do is that, and that's very interesting work, especially from Alexander Isayev and Sergei Tretiak, is that you can also predict these parameters here, or for more complicated semi-empirical methods with a neural network. So you would take in like 3D coordinates, and then you would predict these parameters, and basically these parameters would then go into the physical model. So this is a very simple physical model where you just need to do diagonalization, but it can also be much more computationally heavy beyond that.
So they're heavy in the sense that they have more parameters than semi-empirical.
Yeah, I would say so. Yeah, yeah.
Yeah, so how would you add the chemical intuition in your workflow in designing this advanced, like also hybrid sort of like models, or even like, for example, in the generic algorithm, I would suggest like you know about a fragment that has a certain chemical composition, some certain chemical property, but what else?
Yeah, so I think in this, like in the case of the semi-empirical models, I mean, if you just do pure machine learning, you say, okay, I have this, I have some functional approximator here, and then you just say, okay, I trained this with enough data, and then it approximates my Schrödinger equation solver or something like that. So I mean, already by saying that, okay, we know a bit of quantum chemistry, we know that we can make these approximations. That's already adding quite a significant amount of chemical information into the model. So I mean, that's maybe like you would add the information in the sense of some kind of structural prior or something like that. But maybe in terms of like, okay, what is the chemical fragment space that we're working in? That's also quite a lot of chemical information involved there, in the sense that basically this form, the database, it comes from experiment. So we know that all of these molecules have been made, for example. So that also enforces, I mean, it severely limits the space we are working in, but it also gives the advantage that they are potentially possible to synthesize, because similar molecules have already been synthesized before. So I mean, but otherwise, I mean, people talk about like priors for Gaussian processes and so on, but I've never seen like some application where someone actually puts their intuition into these priors, but it's an interesting question. Yeah.
There's a question online about what you use as a measure for synthesizability.
Yeah, for the synthesizability, we use like a composite measure here. So it's based on 3 different aspects. It's based on the one which is called the SA score, which was like developed for the pharmaceutical industry at Novartis. Then I think it's the RA score, something like that. I think that's Connor's or... Yeah, okay. No, I think we're actually using Connor's is this SC score. And then we're using also the size of the molecule, I think, like the molecular weight. So it's like a composite measure.
Right. And so you mentioned in the beginning that when you start to use a measure, it ceases to be a good measure. But here, so in your exploitation phase, you're sort of like pushing this problem onto your uncertainty estimate.
Yeah, so something we also see with so we actually cannot calibrate these models also to see that, okay, the uncertainty is correlated actually with the predictive accuracy of the model. So we are still kind of staying within, let's say, some acceptable bound of the accuracy. And this is also something that we can then also validate in the sense that, okay, we actually do the simulations for the candidates which we get in the end. And I think it was only like 1 or 2 or something like that we actually need to discard. So the amount of false positives is not super high in this case. So I think that basically has to do with this fragment approach, that we're staying within the fragment space, and then we're still somehow acceptably within the applicability domain of the machine learning model.
Another question?
Is that form database that expanding and people putting more structures into it?
Also, the formed database that's generated by the group of Clémence Cormenboeuf. So there was a PhD student in our group who created that. So now he has graduated. So I'm not sure if it's going to be expanded in the short term. So I think what they basically did here was to mine crystal structure databases. So yeah, so it's maybe not okay. I mean, you would need to redo this every X years, but it's not like it's going to be a lot of new molecules which are added every year.
About the generative models that you're using, you said, of course, that you want to focus on the scoring functions, but I see you're using a lot of how do you call genetic algorithms again. Like, is there any reason why you would prefer them over, I don't know, like deep learning methods that we have right now, or is just that you prefer them for some other reason?
I mean, I'm personally, okay, we have some research in my group. We're working, for example, with diffusion models now, like language models and so on. I think there's basically nothing wrong with these approaches, but I see them more as tools. I mean, if you can get the job done with a genetic algorithm, that's kind of good enough. And there's also one big advantage with the genetic algorithm in the sense that usually you don't need any training data to run them. So if you want to train like a diffusion model, maybe you need like thousands or tens of thousands of data points to do that. And with a genetic algorithm, you can have like 0 data points and you have a very good notion of which fitness function you should create, and then you can just start running it. And they are also quite lightweight computationally. So I mean, there's even some people, there's like a paper now by Hernandez Lobato, where they say that, okay, genetic algorithms should be kind of a baseline, which are you compare to when you introduce like any more advanced method. So they say that in principle, you should be able to beat the genetic algorithm baseline before publishing or something like that. No, that's their conclusions. I mean, I think there are models that do that, but not all models. So, yeah.
Yeah, I suppose that another reason for this is that if you know that what's building blocks that are interesting, that you want to confine yourselves to as in particular domains, it makes sense to use a model that more sort of easily incorporates the combination of these substructures with each other. I guess you could formulate a very complicated like Markov decision process that would take into account all the possible elements in your library, add this substructure, add this substructure. Do some reduced representation, but I think it has its.
Yeah, I think this. I mean, if you look at this, like junction tree variational autoencoder from Jackola and Barzilai, I think it is. I think that also works basically in a fragment space. So it's also possible to work in these spaces also with deep learning models, but then you would need to train them. So that's maybe a challenge. But I mean, in this case, you might say, okay, but we actually have this form database, so you could also train a model on that. So, yeah.
So there's a related question to what one just asked online, whether you can talk a little bit about whether there's any potential improvement that you can imagine by using a reinforcement learning approach compared to these approaches that you're using here. There's any conceptual advantages?
Well, I think, I mean, reinforcement learning, you would still need to have some kind of function which provides this reinforcement. So I think it basically would have kind of the same potential weaknesses. Then I think, I mean, reinforcement learning methods in the sense of like reinvent, for example, has been shown to be quite, I guess you're using graph invent now and so on. So it's, and reinvent, so I mean, they are also shown to be quite efficient and sample efficient and so on. But I think, I mean, they would still need to rely on this somehow, some property predictor to steer the reward.
Any other questions for Kjell? questions online? Otherwise, I think we should thank Kjell for one of the talk. Oh,
Exactly. Let's see. Should I disconnect?